This is Lecture 7, Regression Part 3. By the end of this lecture, you should be able to identify the assumptions of ordinary least squares regression, know how to identify heteroskedastic errors, know how to identify autocorrelation, and know how to identify multicollinearity. Recall that the equation for a regression is dependent variable hat equals b hat times the independent variable plus a hat plus e hat. Remember that e hat equals the actual value of our dependent variable for an individual observation minus the estimate of our dependent variable for that observation. Now, after calculating all of our errors for a particular regression model, if we take the mean of all of those errors, the average should be 0. Why? Because our regression models assume we perfectly estimate our dependent variable on average. Now, our regression models will overestimate and underestimate particular observations, but all of those overestimations and underestimations will cancel each other out, leading to an average error of 0. What is very important to note, however, is that even though the math always works out and we always get an average error of 0, we shouldn't necessarily be confident in our results. When we use ordinary least squares regression, the regression model assumes that we have included all the relevant independent variables in our model, and as a result that all of our independent variables collectively help us predict our dependent variable. And if our model makes an error in predicting, we assume that error is random. Something happened for a particular observation that was a random event that changed the value of the dependent variable. For example, let's say we're running a model using survey data where we use party identification as the dependent variable and income as the independent variable. For one particular observation, the survey respondent accidentally chose the wrong answer for their income because they took the survey too quickly. For that particular observation, the model might incorrectly predict the respondent's party identification because they gave the wrong information about their income. This is a random error. It is not something that happens to every respondent. Regression allows for a random error like this. Of course, we never have perfect models. We never have every single independent variable in our models that should be in there. As a result, our errors are not random. Our errors become predictable for certain observations. This leads to the second assumption of regression, homoskedasticity. This means we assume that the variance of the error term is the same across all values of our independent variables. This picture illustrates a model that meets the assumption of homoskedasticity. In this model, savings on the y-axis here is the dependent variable, and income is the independent variable. These lines represent different values of income. And these normal curves here represent the distribution of the errors for observations at those different income levels. So the regression model made predictions for observations at these different levels of income here, here, and here. And the errors are just the difference between the actual values of savings and the estimated savings from the model. The mean of all of these errors should collectively be 0. And the errors are distributed in a similar pattern across all values of income. They are all distributed like a normal curve. Most often, our regression models violate homoskedasticity. When we violate homoskedasticity, we call it heteroskedasticity. This just means the variance of the error term is not the same across all values of our independent variable. Substantively, this means that our model estimates our dependent variable better at some values of our independent variable and worse at other values of our independent variable. This picture illustrates a model that is heteroskedastic. In this model, savings is the dependent variable and income is the independent variable. These lines here represent different values of income. And these curves represent the distribution of the errors for observations at these different levels of income. So the regression model made predictions for observations at these different levels of income here, here, and here. And the errors are just the difference between the actual values of savings and the estimated savings from the model. Now, the mean of all of these errors should collectively be 0. But the errors are distributed in a different pattern across these values. The regression model is really good at predicting savings when income is low, as illustrated by this thin distribution here. The mean of the errors is low, and most of the errors are close to that mean. On the other hand, the regression model does a poor job at predicting savings when income is high, as illustrated by this flat distribution here. The mean of the errors is higher, and there are a lot of errors that are even higher than this mean, illustrated by the more flat distribution. Heteroskedasticity is a problem. We don't want it in our regression models. While our coefficients b hat should be close to predicting the true coefficient b between our independent and dependent variables, our model is inefficient. Our estimates are less precise, meaning our error is larger. And if our error is larger, we are less likely to get significant results and our R-squared is reduced. In your graduate methods courses, you will learn how to identify and deal with heteroskedasticity in your models. The third assumption of ordinary least squares regression is that the independent variables have a linear effect on the dependent variable. In other words, we assume that the effect of our independent variable on our dependent variable is the same across all values of the independent variable. This assumption is called linear in the parameters, which means that our b hats are the same across all values of the independent variable. The b hat does not change. Or in other words, the effect of the independent variable on our dependent variable is the same across all values of the independent variable. However, we may have a theoretical reason to believe that our independent variable does not have a linear effect on our dependent variable. Instead, we might, for example, think our independent variable has a positive logged effect on our dependent variable. If that is the case, we think that at lower levels of our independent variable, the effect of the independent variable on our dependent variable is strong. A small change in our independent variable here leads to a large change in the dependent variable. But at higher levels of the independent variable, a small change in the independent variable here only leads to a small change in the dependent variable here. Another way our independent variables can have a nonlinear effect on our dependent variable is called an interactive effect. With an interactive effect, the effect of our main independent variable on the dependent variable depends on the level of another independent variable. So for example, imagine we have two independent variables. The effect of the first variable on the dependent variable is positive when the second independent variable is 0, and negative when the second independent variable is 1. So the effect of the first independent variable depends on the level of the second independent variable. In your graduate methods courses, you will learn how to run and interpret models with logged independent variables and interactive effects. Next, the fourth assumption of ordinary least squares regression deals with time series models, where we have multiple observations for our subjects over time. In these models, we assume that the error term is not correlated with time. Alternatively, we assume that the value of our dependent variable in one time period is not correlated with the value of our dependent variable in a previous time period. In this graph, I plotted the errors against time. As you can see, there's no relationship between time and the errors. If I drew a line through the middle of these points, the slope would be 0, indicating that time has no effect on the errors. When we violate this assumption, it is called autocorrelation. The error term is correlated with time. It is not random. This graph shows one potential way errors can be correlated with time. As you can see, as time increases, the errors get larger. In your graduate methods courses, you will learn how to identify and deal with autocorrelation in your time series models. The last assumption we will talk about is the assumption of no multicollinearity. Multicollinearity deals with models with more than one independent variable. We did not go over these types of models in lectures 5 and 6, but you will in your graduate methods courses. With no multicollinearity, we assume that the independent variables are not related to each other. When we violate this assumption, we have multicollinearity in our models. That means our independent variables are correlated. When this happens, it's almost like we have the same independent variable twice in our model. As a result, we are less likely to get significant results. We cannot tell which independent variable is influencing the dependent variable since they are so similar. In your graduate methods courses, you will learn how to identify and deal with multicollinearity in your models.